Hello, my name is Eric Turner, and I'm going to be discussing Lab 2, Even More Tape. So just an introduction and a background to some of the ideas that are important to understanding this lab is that everyday objects acquire excess charge via interactions with other objects, even when they're neutral. Like charges will always repel and can sometimes overcome or balance out other forces, and that's going to be important later on. Coulomb's law is necessary when relating charge to force. That's the top equation on the left side of your screen. Newton's second law is pivotal to evaluating this lab. That's the most important part in evaluating the math, and that's F equals ma. Newton's third law is what allows us to properly analyze the complex forces at hand. This is important to making some big assumptions that allow us to do the math that we do. So some of the expectations that we were asked to think about was that while you rip the U-tapes apart and you give them a positive charge, do you think they would repel one another? And it was confirmed that they would repel because of the same charge. And the second expectation is, would you expect it to be positive? And it was, because it was attracted to a negative charge, which was a pin charged by rubbing a shirt on it. Some of the critical assumptions and approximations we have to think about. To properly look at the math for this lab, we have to think about the charge on the tape as being uniformly distributed along the length of the tape. The effects of the other charges on the same piece of tape can be ignored. So the idea that the charge on the same piece of tape won't alter the effects of another charge on that same piece of tape. Each U-tape has approximately the same charge, and that we can ignore air resistance. Just some of the data that I collected. You have the length of the tape, mass of the tape, force of the gravity on the tape, which was 0.001991 newtons. And that's important when we try and find the electric force on the top tape. So getting to the code, which is really what kind of made this lab unique from the first one. Instead of looking at it like a point charge, we're gonna this time look at it as a line of charge. And this is the most crucial step to the code, where we iterate through and we're summing the electric fields of each individual charge on that tape. Like I said, this is the most critical part of the code, and without it, you wouldn't be able to look at it as a line of charge. And you'll see the results of this in this slide, where those green arrows are kind of the sum, or not the sum, but each individual electric field made by the charge on the bottom tape, which is represented by the blue spheres here. And as you can see, the blue, there's no clear distinct line between the two, and that's because the separation distance I observed was rather small. And as you can see, the magnitude of the electric force and magnitude of gravitational force are, for all intents and purposes, the same. And we can expect that because they have to balance out. So now to look at some of the critical questions that are important to ask ourselves at the end of the lab here. What if we treated the tapes as a point charge? And that's what we did in lab 1. And you'd find that it'd be really inaccurate, and that the line charge model would be more accurate to how nature behaves. And the reason that applies here is the tape isn't spherically shaped, and it's kind of too large to be thinking at it as a point charge. There's too much going on. It's too complex to think of it as simple as a point charge. So it's more accurate and more accurate to nature if we model it as a line of charge, which we did here. And the summary at the end of the lab: all objects, charged or otherwise, are subject to electrical interactions. Making some assumptions, you can easily estimate the amount of charge on a subject and field it produces. And as we just stated, the line of charge model is more accurate to how nature behaves than the point charge model for this scenario. Thank you.